Okay. We're excited to have you here, and we want to welcome you to Flatiron School's Intro to Data Science Linear Regression Models. My name's Catherine Sommerfeld. I'm the Director of Marketing Campaigns and Events here at Flatiron School. Part of my team's job is hosting free introductory workshops like this evening's event to give you the opportunity to meet some of our instructors and get a better feel of the Flatiron School experience. A quick reminder again, we'll be using the chat as our main source of communication, so make sure that you have it set from host and panelists to everyone so we can chat together. Without further ado, I'd like to introduce our host for the evening, David Elliott. He's one of our lead data science instructors. Take it away, David.
Hello, welcome. I'm looking forward to this. I'm watching all of the locations flip through, and it's really cool. I am here in Seattle, so shout out to my Seattle crew, but I saw a bunch of places go through. I lived in Chicago for a while. I saw that. I saw Rwanda come up. I've been to Uganda, so close, and I saw Amsterdam come through. I visited Amsterdam for a while. That was fun, and some of the other ones. So San Diego, I had a client down in San Diego. I spent 6 months traveling down to San Diego from the winter wet of Seattle, and it was one of the best winters I've had. So sunshine dollars are no lie. Why don't we just go ahead and get rolling on this? So we are going to talk about simple linear regression today. A little bit more about myself. Like I said, I started out as a software engineer, as a consultant, traveling around the country, did that for about 10 years, got really burnt out on 45 plus weeks a year on the road and quit. And I needed to do something. And then I had been teaching motorcycle classes on the side. And it's like, hey, maybe I can make this a gig. You've heard the phrase that if you do what you love, it's never a job. Well, I learned that is a completely inaccurate phrase. There was a lot of work behind it, but it was a lot of fun and I really enjoyed teaching. But I got to the point where I was at the top of what I could do without moving or working for the government. Neither of those were things I was interested in. So then it was, now what? I started learning about this data science thing, and my degree is in math, in particular finite math, and that's a lot of what data science is. And I learned that it's all based on linear algebra. I'm like, oh, this will be easy. I was very wrong. Thankfully, the math gave me a basis to work on, and the software engineering gave me the code background so I could concentrate on things like statistics. I managed to get through high school and college without one single stats class. So my boot camp was a bit of an experience. And stayed out in the industry for a little while after I graduated my boot camp, and just was missing something and realized that I really, really enjoy teaching. I enjoy the interaction. I enjoy that part of it. So I was able to find a way to combine data science and instruction and teaching. So here I am. And with that, let's get rolling. I'm going to periodically pause for questions and see if any questions come through. And Catherine will pass them on and we'll try and answer them as we go. I will also be around at the end of the presentation for any questions you have. We're going to look at some slides first to kind of get you the theory. And then I do have a short little Jupyter notebook where we do the actual Python and look at the actual code about what to do and how to do it. And hopefully show how cool some of the things are and how amazingly easy it is to do some of this stuff with the modern tools. Excellent. We're going to cover why linear regression. We are specifically covering simple linear regression. That is basically just one variable and one target. We're not going to get any further in depth than that. We are going to talk a little bit about inference versus prediction, and we're going to talk about why a line can be a model, and then we're going to jump in to look at an example. Linear regression is kind of the very first thing we teach here at Flatiron. It's the very first thing. We tack it on the end of our stats section because it is a statistical method. You're looking at variance, you're looking at covariance, you're looking at Pearson's correlation, you're looking at all these statistical things we learn, and we can actually build a model. We first use it for what we call inferential statistics, which is trying to get information about the data set. You know, what features are important? Where's it going? How are we doing this? We then build on our knowledge of linear regression and work it into a predictive model. Can we actually predict something from our regression? And that's the introduction to machine learning. We spend a lot of time with linear regression, really understanding the how and the why, and trying to figure out what's going on there. And we're not going to spend too much time on the math, but we'll show you a little of the overview, and we'll show you also what we call the closed form, some of the linear algebra behind it. Oops, that went way too fast. Sorry. Dunk. Talk about what simple linear regression is. It's simply using a line. It's literally a line through your data, and we'll see some graphic examples of that later on. We call this regression because what we're trying to predict is continuously valued. For instance, house prices. That's something that varies. It's a continuous line. Something that would not be a continuous line would be like a class of something. Is this person going to churn from the credit card, or are they not? It's a yes or no. So it's a different way of looking at it. So linear regression, a line that predicts a continuous variable. One of the beautiful things about linear regression and why it can be so fast and efficient on a computer is this closed form solution. And we're just going to briefly look at it. This X transpose X inverse is the pseudo inverse, as it's called. It's much easier to calculate than a standard inverse. Times X transpose times Y. Those are all vectors or matrices to give us our betas or our coefficients. So it's a very quick, easy, efficient method to do it. But we're not going to really talk much more about that. I just wanted you to be aware of some of the thing. Linear regression's a closed form algorithm. Examples. As population, so do housing prices. That should be pretty clear. That's a direct and positive correlation. A negative correlation here would be trees decrease, CO2 goes up. Well, they are probably correlated, but just negatively. Inference is looking at those patterns. What can you get? What can you infer from the data? How can you approach it? What can you do? One of the beautiful things about linear regression, and we'll show you this later on, is that the coefficients that we come up with have actual meaning. I can look at that and say, oh, the model has figured out that this particular feature is very important. The coefficient is much higher. If it's positive, it's positively correlated to the target, in this case, housing price. If it's negative, then I can say trees decrease, CO2 goes up. So you can really get a lot of information by running one of these regressions. Why don't I pause there and see if there are any questions? It looks like we got the spammer out of that. So I'll pause for a second here, see if any questions come through.
I haven't seen anything specific yet, David.
Cool. Brief note on that repo that Catherine sent out. That is, it's one of our repos. It has the Jupyter notebook, so you can follow along or look at it later. It also has a copy of the slide deck for reference. Cool. Off we go then. Here's an example of a data set, and we're looking at specifically one feature. Miles to gallon versus weight. And you can kind of see that, hey, there is sort of a slightly linear, maybe it's a little bit curved. Here's a better example of just some data points in talking about how to fit a line to something. That's the line of best fit. And we'll talk a bit more about what the best fit line is and how we figure that out. So some of you hopefully remember the formula from a line way back in high school. Y equals mx plus b. That's exactly what I have here. Y hat, which is short for our prediction, is equal to beta 1, which is our first coefficient, plus beta naught, which is our intercept. Y equals mx plus b. Same thing as a formula for a line. Now, we also have to take into account error because no model is perfect. It's just not going to happen. So we define error as the error of our line is the difference between our actual target, y, minus our prediction, y pred. And we also want to get rid of our sign, because you can be both above and below the line, by squaring everything up. And the reason we do that instead of absolute value is because I can then take the square root of that and use that in something intelligible. And I will also be showing you that later. So the formula for linear regression is pretty straightforward, and these are the error terms we use. Check here. Cool. So take a moment here. Which line's the best fit line? Is it black, blue, red? How do we figure out what our best fit line is? That's kind of the big question we're looking at, and we're trying to figure that out. Our goal is to minimize our error. Our goal is to minimize this number. How do we do that? Here is the math kind of behind it. RP is Pearson's correlation coefficient. Y bar, or X bar and Y bar, are the means of our X. So we get all of our X points, take the mean of it, and then it's each individual point minus that, the sum of those errors multiplied, divided by this. That's how we get our Pearson's coefficient. To find beta naught, our coefficient of our X, Pearson's coefficient times the standard deviation of Y over the standard deviation of X. Please note, this is not sample standard deviation. This is population standard deviation, so n, not n minus 1. Find the intercept. It's simply this. Let's take a small example and just show you the math behind it so you can appreciate how complex these equations can get, and how, when you see it done on the computer, how amazing our computers are and what we can do. So with for just 3 of these, our 3 points, we calculate X mean, calculate Y mean. Pretty straightforward, X bar, Y bar. Then we have to calculate these different products that we're going to be using to calculate Pearson's correlation coefficient. So now I've got these. Now we can start plugging them into formulas. We've got that, which is 16. We've got that 8, that 38. This reduces down to 4 over root 19. In particular, this example. And calculate the standard deviation for X and Y. And we can put it all together. So our beta 1 coefficient is 2. Cool. But as you can see, that's only 3 data points, and that's a whole lot of calculations just to get that. To get beta naught, our intercept, Y bar minus beta 1 times bar X is equal to that, rolls out into that. So for those 3 data points, that's our formula. Our predictions are equal to beta 1x plus beta naught is equal to 2x plus 1. That's pretty cool. And that's our line. That's how we got our line of best fit. I'll pause there to see if there are any questions come through.
We've got a few. So the first says, I know you said we'll only be going over linear regression, but does Flatiron School teach other topics as well?
Oh God, yes. We take linear regression and run through it into multiple regression. Then we build on the linear model and talk about logistic regression. Logistic regression is the introduction to our classification algorithms. We'll talk of things like k-nearest neighbors, trees, random forests, extra trees, boosting, bagging. We get into, and those are just sort of our models there. We also talk about advanced topics like natural language processing, time series, neural networks, deep learning, we go the image classification. So we spend a lot of time with convolutional neural networks as our introduction to deep learning and recommender systems. So we talk about a lot of models. We spend the most time on linear regression to really build on those concepts, but then we build on that and take it and go.
Okay. We have another question that I think builds on this a little bit, which is just why do we assume linear? What about other relationships that are non-linear linear or multiple variables?
That is an excellent question. I will talk a little bit more about that at the end of this because that is very insightful. And yeah, we'll discuss that a little bit.
And one more, can you explain how data science and software engineering work together?
Sure. I am not anymore a software engineer. My skills are out of date. When I talk about things like memory management, tracking pointers, taking care of all of that, I don't do that anymore. Software engineering, however, builds the back ends of all of the modules we use. The people with the deep software engineering, the numerical computationalists, I think I said that right. They're the ones that build the tools we use. They don't look at the tool and go, they say, hey, the tool is performing. They don't look at the result and interpret it. That's my job as the data science. So I work with software engineers to make sure we're getting the tools we need. I don't build the tools, I let them do that. And they don't interpret the data, they let me do that. So they are fairly closely integrated. And if you can start seeing the line can start getting really blurry really quick. So hopefully that answered that question about the questions of that. And so how do I define linear versus that's a line? We're going to stick for simple linear regression. What we're doing, we're calling that. I will address more about lines later.
I've got one more, David.
Yeah.
How long does it take to learn all this math? Do you need prerequisites in calculus or other advanced math?
It helps. We do get into calculus because we start talking about derivatives and partial derivatives, and we talk about gradient descent. We get into linear algebra when we talk about how this is happening on the back end and what the matrix manipulations are doing. It really does help. It is not a requirement. Knowing how to derive the partial derivative of our loss function will not help you to interpret what it's doing. We cover enough math so you understand what's going on in the back, but it is not a requirement. It just helps. To be successful at one of our boot camps, I say there's 3 things you need. You need a background of math, you got to have some stats, and you got to have some programming. Without any of those, it's going to be challenging. All 3 of them, it'll still be challenging, but your learning curve is much less. Yeah, cool. The slides are in the GitHub repo. Awesome. I'll keep rolling then. This will hopefully also help. We're looking at sum of squared errors, which is the sum of every single error in our predictions. And we're trying to find where that is the least. And if you look at what we got here, slope looks like kind of somewhere right around in there. So we had I can't remember, that was too long ago. Okay, 2x plus 1. So if you look 1 and 2, so if you kind of look right in there, you can see where that is, that slope of our error function is the lowest. This can be called a cost function or a loss function. Just getting a little bit technical here, and this is what we try to minimize. That's what that looks like. Here's some of the things we don't cover. We're not in this workshop. I don't want to take the time. Variance and covariance are important to linear regression. I just didn't want to jump too far down there. We also don't cover the assumptions of the linear model. There are 4 or 5 assumptions depending if we're doing simple or multiple. And I'm just not going to bring them up. And we don't talk about the question that was brought up. We don't talk about bending the line. So if you recall, let me flip through these. I apologize because this is a good illustration like that. That's not a straight line. Well, I can bend that line. I can add a term. I can add a feature, maybe throw in a squared term. So that does start bending the line. So a line isn't always going to be straight. You can bend it in different ways. And when you start thinking about three-dimensional data, that's where things get really interesting. I'm still using a line, but that line may curve all around if I throw squared terms or cube terms or other things in there. It's not always just going to be solid and straight. And we also are not going to get into more than one feature or more than one X variable. That's just, we cover that extensively in the boot camp. We just don't really have time to do that here. Pause here for questions.
I've got one, which is what type of visualizations are the most common?
What are you trying to show? That's my students hate this answer, but I say it depends. What are you trying to do? What are you trying to show? What are you trying to illustrate? If you're trying to illustrate the distribution of some features, a histogram is going to be better than a scatter plot. That doesn't really, I can't get how many from the USA are out of there. Is that 100, 200, 300? I don't know. So this is a really bad example for showing me distributions or counts. It's really good to see a pattern there. But another example would be distributions. Is my distribution normal? Do I have problems with my data? Well, I need a kernel density plot to look at something like that. So the answer to that question is it depends on what you're trying to do. Scatter plots are used a lot because it helps us humans to see if there's relationships. I can look at that and go, oh, there's kind of a curved relationship there. Okay, that makes sense. I can play with that. To answer Christina, we use Matplotlib and Seaborn. We do things exclusively in Python right now. We'll be adding Tableau content soon, as that is gaining traction and market share. So currently it's Python and the libraries there too, pertaining there too, and we will be adding Tableau stuff in the future. Can I recap everything I just said? Linear regression is using data points to find a line that best fits all of those data points to make predictions. And I think that might be the simplest way to put that. You all hopefully have this. There's a link in the presentation should you need it. And with that, I'm going to switch over to the notebook. So I'm going to assume not much Python knowledge, and I will be briefly talking about what the code is doing, so you have an idea with it. In Python, you have to bring libraries that aren't part of base Python in so you can use them, and that's what I'm doing here. I can import these. Here is our inferential linear regression model. Here is our predictive linear regression model. They're doing the same thing, but the tools are designed for different uses. sklearn is the main machine learning library we have in Python, and everything is set up the same way in terms, it's specifically designed for predictive. This is much more inferential. And visualizations, and this just makes data easy to handle. So first thing I'm going to do is there's this neat little library. I'm going to just randomly create a data set, because I don't want to import anything. I didn't import. My students always laugh at me. There's always an over under on, did he run the imports for the first line of code? So this is just making the data usable in a form that I can use it at. And here I'm creating this, which is just a data frame that lets me look at things in a nice, easy way. So the numbers are basically just numbers. Humans don't process that well. That's not telling me anything. Let's look at it. We're going to do a regression plot, which is a scatter plot with a line of best fit through it. So that is what our data looks like. All the blue points are stuff that has been generated. We have our X on the X-axis, Y on the Y-axis, and this is what it looks like. This line is our line of best fit. The lighter red is the 95% confidence interval, which we're not really going to cover right now. So stats models is a great, has many statistical packages in it. It's very solid. It's written by statisticians, and you can tell that because they use terms like endogenous and exogenous. What are those? Fortunately, they also define it for us non-statisticians. I'm looking at you, Catherine. So basically, endogenous variables is the Y, the target. Exogenous, exog is our predictors, our features. You'll hear these called predictors. You'll hear these called features. You'll hear this called target. You'll hear this called what we're trying to do. But that's general brief terms. So I basically have to set what my variables are, and this is adding a constant because we need to find our intercept as well. It doesn't do it automatically. So with just that line of code, I've created everything, and with this line of code, it's running the calculation on 1,000 data points to get all of our information. One of the nice things about OLS and stats models is it gives us this really handy summary with a bunch of information. There's a lot there. This post does a really good job of stepping through and breaking things down individually, what's going on, what they all mean, how they mean, why they're important, what they're doing. A bunch of this stuff like the omnibus, the kurtosis, Durbin-Watson, and Jacques-Barra are important when we talk about the assumptions of linear regression. Again, don't really have time to cover those. But you now have a place to do that. So let's look at this. Here's my coefficients, X and Y. So if you remember what we're doing, here is my formula that is the best fit line for this data set. Let's double check that. What I can do is I can look at the results, and I can look at particularly the parameters into there. And this is telling me, look at the first parameter. So fun thing about Python doesn't believe 1 is the first number. It is 0 is the first number. We call this Python indexing. Is there a difference? I'm going to get this real quick. Difference between a negative and a positive coefficient? Absolutely. A positive coefficient means as I increase X, I'm going to have a positive increase in Y. A negative coefficient would mean as I'm increasing X, Y is going to be going down, not up. If this were reversed where the line was looking, going from top left to bottom right, X would have a negative coefficient. So let's just double check, make sure we got the results. Look at that. There's our intercept. I can pull out the beta 1 value, and I can make predictions on that by saying I'm going to take this times the parameter, results params, and put that in the data frame. And I'm going to calculate these residuals. Residuals is also a term for errors. What is left over after my regression? What is residual? What is the error? How far off am I? And I can calculate that by simply saying, take our actual values of Y, subtract from that our prediction. And make sure I execute the cell. And I can see, okay, there was the actual value of Y. There's my prediction, so residuals. And you can see some of them look to be kind of large. Quick question from, I'm going to butcher this, Johan. I'm not sure if it's Johan or Jojan, sorry. Is Matplotlib still default graphing library? Yeah, Seaborn's nice. There's some really cool stuff coming out that's interactive, but Matplotlib is a great start. We use that as the base because so many other libraries are based on Matplotlib. So we have a question now. Is this a good model? Don't know. There are two ways of looking at that. Back up here, we have this thing called R squared. R squared is the percent of the variance in our data that is explained by our model. how much of this scatter, how much of the variance in our data is explained by that line. In this case, 65.2%. Gonna have to say it's not that good, which if you look, well, it may not get any better just with how the data is, but that's one way of looking at it. I can use this to compare models. This is a really good way of looking at model 1 here, or comparing to model 2 or model 3 as I'm making changes to the model and how I do things. Another way of looking at it is, well, actually, what I want to know, I don't really care about explain variance because it's handy. How accurate is my model? How well is my model actually performing? Mean squared error. We take our error term, hopefully this looks familiar, square it to get rid of any sign, any kind of sign, and then divide it by 1 over n to get the mean. This is telling me how big the average error is. Squared up, by the way, so it's a big one. You can calculate it by hand. I can take that particular column. This is the Python for squaring it. I can sum all that up and divide it by the length of my data, and that gives me a mean squared error of that. That's double error or squared error. That's not really interpretable. How do you do that? So then we have a better tool, root mean squared error. So I can take the mean squared error and take the square root of that. Now that is something I can do because this is the square root of the squared. It's in the same units as our error. So I can say on average, each prediction here is 11 y units off. Is that good? Is that bad? Well, that's what you have to figure out. Another way of putting this, if I'm trying to predict house price and my root mean squared error is, say, $10,000, I can say the average prediction is off by $10,000. So root mean squared error can be very beneficial for determining model performance. It's a good way of looking at that. But I don't want to do this by hand. That's illustrative only. Here's a nice little library where I can just input what it is I want. That gets me mean squared error. And by telling it to not return squared data, I get the root mean squared error. So there we go. My libraries work. That's nice. Much fewer lines of code. I'm of the opinion if there's a library, use it because it keeps human error out of things. I only have to worry about 2 things here, not all that code. The less I'm touching code, the better off everything is. That's our inferential model. I'm going to stop here, pause for a little bit, see if anybody has any questions about what we've covered in terms of the inferential side of linear regression. Best way to learn stats. I have a book. I worked with another instructor. She had her doctorate in statistics, and I asked her that same question. It's called The Cartoon Guide to Statistics. It was actually a textbook in one of her classes. I read that. I read it again periodically. Yeah, Cartoon Guide to Statistics. It is a great introduction to some of the basic stats, and it gives you enough of a grounding on what's happening, what they're doing, how it works, that the other stuff can work from there. Catherine, I'd be curious if you have a recommendation for a stats resource.
Other than my professor, who's fantastic, we haven't been working out of a book. We've been using entirely stuff that he's put together for us. So that's, yeah.
Well, that wasn't helpful.
We have a textbook resource, but I literally have not looked at it once this semester.
Cartoon Guide is a really good place to start. So we'll just leave it at that. I don't see anything else coming on. So scikit-learn is the machine learning library for Python. This is, you can see everything. It's got all sorts of things. To answer real quick, MSE or RMSE, both are accurate and valid predictors. RMSE is interpretable. the squared error really isn't interpretable. Or if I take root mean squared error, I can interpret that to a stakeholder. I can say, here's our model. It has a root mean squared error of $10,000. So I know every house price that I predict with this model will be on average off by about $10,000, either above or below. So they're both valid measures. Root mean squared error is readable and interpretable. Back to sklearn here, you can see there's a whole bunch of different things. We're going to deal specifically with regression, but this is all set up for prediction. Cool. So I have to instantiate it. For those of you, that's a class. I got to create a class. I got to make an object there. Create my X variables, create my Y, and fit it. And that's it. That one line of command here, one line of code, this is my linear regression. It did all those calculations on that thousand data points. We can look at the coefficients. We can look at the intercept. And this is where sklearn differs and is easier. It actually has a predict function, so I don't have to go do any math. It can simply say, hey, take my data set, give me my predictions. I'm going to still do the linear regression differences so we can look at it. And I mean, you can see they're pretty much the same. I don't know how many decimal places out before it changes, but these are using coefficients. I mean, look how many decimals there are on that. So it's using a much more accurate number, but it is pretty much the same. So kind of proof that it works. We don't have a summary, but I can get my score. In this case, that's R squared. So that's 65.18. If you recall, aligns pretty much dead on with that one. Cool. And if you looked at the intercept and coefficient, it's pretty much dead on with those. Go down. And we're just going to use the mean squared error, root mean squared error, call it that. And there we go. Pretty much the same numbers, so they both work. Let's see what that looks like. I have plotted in the reg plot, same thing we did before, but now I've added a line where my X values are X and my Y are all of these Y preds. And all of my predictions fall directly on that line, which should make sense, should be clear. So what does it look like when I have a new data point? I'm going to just randomly create a new data point. I'm going to get that new prediction. I'm going to predict using the model we created. I'm going to send it this new data point and say, hey, what do I get from that one? And let's look at, so X is the actual data point where it falls into the data set. And there's my prediction, again, directly on the line. And that's R squared doesn't really tell you how accurate the model is. It kind of does. It tells you how much variance is being explained. We're not going to get into the variance bias trade-off in this conversation, but it's a good measure of looking at it. A higher explained variance, the better performing your model is generally going to be. So that's simple linear regression in a nutshell, as well as how to do it in two different libraries, one inferential, one predictive, and what your predictions look like. Again, what we are not doing is we're not talking about what the assumptions for linear regression are. I'm not going to go in and look. We only have that. I'm not looking to see if there's a linear relationship between X and Y. Well, there is here. We can see it. I'm not looking to see about if our residuals are normally distributed, homoscedasticity or heteroscedasticity. There's a bunch of things we're not going to look in because we don't have time, and that's covered with what we do. Any questions? At a given X, can you count? I'll get to you in a second about training and test. And we'll yeah, nice, good catch. Given X, can you count the Y points near, and if more are above the line? Not with linear regression. That's not how that works. There are models that will do exactly what you're doing, and they're called boosting models. Boosting models will look at the errors of a previous regression and do something with that. So with what we have here, no. Is it possible and done? Yes. And the other thing there is training and test data sets. I always wonder if I'm going to get pinged on this. He is referring to I'll just say this. Here's my test data set. How about that? Does that work? I'm not going to cover that a whole lot now. We definitely discuss that when we're talking about train test split and validation sets, holdout sets, and some other stuff in our course. But briefly, the idea is you take a data set called training and you train your model. You fit your model on your training data set. And then you take a data set called test that the model hasn't seen and run this unseen data through it and to see how it performs. And you can compare the two. And there's a bunch of diagnostics and back about how your model's doing based on trained test scores and a bunch of other things. So just didn't really want to get into it in this lecture. Nice catch. Cool. Any other? No, we don't get it for your. I can never pronounce that word. Dang it. I studied German, not French, so French just baffles me every time. Yeah, that one. No, we don't really cover that in our class.
David, I was busy copying and pasting. Did you see the question about correlation in the Q&A?
I did not.
There's one that says, how about correlation? Like I have a new variable and want to see what other variables it most closely aligns to.
We talk about that extensively. That is one of the assumptions of multiple linear regression, is that your variables are not highly correlated or independent. And we get into looking at Pearson's correlation coefficient to determine that. And then we take that information and figure out how to deal with our multiple variables. But that is definitely part of multiple linear regression when I have more than one X value. And if they are correlated, significantly correlated, we do go over how to resolve that correlation, how to resolve the multicollinearity, and what that means.
I've got one more. Why would you split the data set to backtest the model? Is it possible in this day and age of computers that the computer runs the model computations wrong and therefore you need to test it?
It's to simulate unseen data. It's to simulate brand new data. The model has trained. So when I say train or fitted, the model looks at all of these data points to get these values, to get those coefficients. I want to know how that performs on unseen data, because that's the whole point of this. It's to build a model that's going to get data coming into it. Here's new data. Here's new data. What's the prediction? What's the prediction? So to simulate that, we divide it into training and test. I would split this into a training set, do my fit only on X train and Y train, for example, and then do a predict. Where did I go? Do a predict on X test, for example. And that way, it's trying to take unseen data, all of these values it hasn't seen, and create predictions. And that's a better approximation or a better metric of how the model is actually performing. Hopefully that answered that question. But yeah, I'm just wasn't going to get into train test splits in this lecture. There we go. That's where I put it. Oh, more questions. Let's see here. This model does not rule out outliers. Since this is a distance-based algorithm, how far away from the line is the error? And this is a regression where we deal with, we have to worry about our distributions. We're assuming normal distribution. We're assuming a kurtosis of 3 and a skew of 0. Outliers have a significant effect. There are many ways to deal with them. Again, we'll cover that there. Is that better? So this model does not in any way, shape, or form rule out outliers. That is something you have to do as part of data preparation. You have to go through and look at that and say, is this outlier really affecting things? Do I need it? How much is it affecting things? Things like that. Good question. Any others that I missed, Catherine?
I don't think so. Just so everyone's aware, I'm also going to grab all of the different book recommendations and see if we can get those included in the email that will go out after the event. If there are no other questions, I'm going to wrap up. I just want to give it a second to make sure everybody's good. All right. Well, thank you again, David, and thank you to everybody who zoomed in to join us tonight. If you have further questions about Flatiron School, I dropped the link to schedule a chat with our amazing admissions team in the chat. As a reminder, you'll receive a copy of tonight's presentation within 3 business days. And if you'd like to see any previous events, head over to YouTube and subscribe. Thank you, everyone.